Hello, everyone. My name is Shergadwala, and my co-author is my advisor, Professor Jitesh Panchal, and we are from Purdue University. Today, I'll talk about human inductive biases in design decision making. So, inductive biases as a term is typically used in computer science domain area where the learner is an algorithm and it is defined as the initial set of assumptions that the learner uses to predict the outputs of given inputs that it has not yet encountered. Now, in context of engineering design, we are considering the learner as a designer in context of an information acquisition scenario where the designer is exploring the design space and acquiring information about how various designs in the design space are achieving the design objectives. So from that perspective, inductive bias is a positive term as compared to the biases that are typically utilized in a negative connotation. And because these inductive biases are required in scenarios where there is high uncertainty and there is lack of prior data, such that then designers need to rely on their prior knowledge, their expertise, and so on to make decisions. And that's why the objective of this paper is to identify inductive biases in sequential information acquisition tasks. To do this, we leverage experimental data sets of these controlled behavioral experiments that we have conducted in the past. And all of these experiments have sequential information acquisition tasks. And so we want to study how human subjects are making these decisions. Across all the tasks, there is an abstraction of the design process, which these human subjects follow. And it is divided into three main activities. So at any step in the design process, these human subjects can choose a design, which we term it as X. And for that design, they can acquire information about how well it achieves the objective and whether the constraints and at that point in the design space they're satisfied or not through experimentation. In the experiment, it's simply by one click, but it's abstracting a real design scenario where designers conduct simulations, prototypes, and so on. And then based on the experiment, they are receiving information about how well the objective is achieved and whether the constraint is satisfied. And that helps them decide whether they want to continue to acquire information and continue these activities or whether they want to stop this process. And this happens sequentially. But in this particular scenario, what we're doing is that we are focusing on just the decision to choose these X variables, and we are focusing mainly on the first time step because the hypothesis is that the first decision will be primarily driven by their prior knowledge, and that will help us identify inductive biases. So from an experimental standpoint, when we are focusing on these variable design decision of choosing X, we have data for every individual of what at each iteration, what values of X did they choose. And we have this sort of data for 6 experimental data sets. So what we are trying to see is similarity of the first decisions that the designers make across various design spaces and try to identify any similarities or patterns in their decision choices. Now, what we find is that in the first case, when we plot the histogram of the first decision of choosing X across all these 6 experiments, we find that participants across these different experiments tend to choose the midpoint of a given design space. So now the range of this design space could be minus 10 to 10, like in this experiment, it could be minus 100 to 100. It doesn't matter. We see that they tend to choose decisions of X, their very first decision, which is not uniform. It is focused in the mid-range. And so we conjecture, we hypothesize that participants probably use a bisection approach to search in the design space. Then, of course, there are nuances in each and every experiment where we can see, for example, in this experiment, there is high search frequency, even on the extreme ends. So let's go into details for that. So in that particular experiment, participants were also given information about the uncertainty of this objective that they're trying to optimize. And they were given a screen where for any value of X that they chose, they got the corresponding information of f of X. But then for the rest of the points, there was these uncertainty graphs that were given to them. And we see that when information about uncertainty is provided to the participants, their decisions are nudged to minimize uncertainty and choose those points in the design space. Like for example, at minus 10, at 5, minus 5, even at 10, we see that it's higher than the rest of the experiments. The other result that we see is anchoring bias, where we just take an example of one experiment here, where what we have done is that we have plotted the initial data point at x is equal to 850 as a straight line, and then the corresponding value that they observe at x is equal to 850 of the function. As that value gets higher, their decision to choose the next x moves closer to that initial data point, and that is a potential anchoring bias. So for example, at x is equal to 850, if I have observed that the function value is 150, my next decision is very close to 850, and that's the sort of observation that we have. We also see these streaks, which show that participants are still choosing values at the mid-range as well, and so we see a combined effect of these different biases taking place. The fourth result is a directionality effect that we observe across these different experiments. So this experiment was a function minimization experiment, and this experiment was a function maximization experiment. And what we observe is that in the minimization experiment, the right side of the midpoint of the design space, participants tend to choose values in the beginning and on the right side, and then eventually move to the left. Whereas in the function maximization experiment, we see that their first choices are more focused on the left side of that midpoint, and then they eventually move to the right, which makes us conjecture about a possible directionality effect, that when the objective is to minimize, they move along the negative x-axis, and when the objective is to maximize, their choices are moving along the positive x-axis. So all these are conjectures that we have preliminarily identified from the data, and in our future work, we require further validation about these inductive biases and how they can be tested in other experimental scenarios, which would help us then formulate better decision support tools as well as computationally model prior knowledge of participants. Thank you.